The next idea we're going to explore is an idea that allows us to do sweep line algorithms in the IO model. So let me just quickly overview one solution for one specific problem that we're going to look at, and this is called orthogonal line segment intersection. We have a bunch of vertical and horizontal line segments, and we're going to find all the intersections. If you remember the third lecture of the geometry part of the course, we looked at the line segment intersection problem, where we had a bunch of line segments and we want to find all the intersections. This is obviously a special case of that. And if you recall, we solved that problem using a sweep line approach. So where we had event points both the top and the bottom, as well as the intersection points. Here in specific problems, since the line segments are vertical and horizontal, we don't even need to have an event point for the intersection of line segments. We can just have an event point for the top and the bottom. And the solution basically works by maintaining a search tree on vertical line segments. Every time we see a top, we insert. If we see a bottom, we delete. And when we see horizontal line segment, we can just do a query on the search structure. Okay. In the internal memory, that will give us a solution that runs in n log n plus t time, where t is the output size, or the number of intersections. Obviously, we can try to simulate the same algorithm in the IO model. Of course, we could even use, even if we use a B tree though, we might get this part with t over b, and we might get this part with log base p of n. But this part cannot be improved. This is because insertion and deletions inside a B tree will require at least one IO. And since we have n event points, we were going to get this factor n without the divided by b part, which is the major part that we actually want to get. So this idea out of the box does not work in the IO model. However, we can use some interesting modifications to make it work. And the idea that makes this work is known as distribution sweeping technique. So now I will explain what distribution sweeping does. So distribution sweeping is essentially based on the distribution sorting, which was, if you recall, what based on quicksort. The idea here is to divide the plane into MOV slabs with such that every slab contains roughly equal number of endpoints. What this means is that if this is my input on the disk, I will pick some x coordinates as my splitters, review the quicksort part of the IO algorithms, or the distribution sorting part of the IO algorithm, to remember this. So I pick these x coordinates as my splitters, and I could split my input into a bunch of sub-problems, where each sub-problem corresponds to one slab. Okay. But here I will need, so the vertical line segments are obviously, they go to this vertical line segment goes into this slab. But I have to do something about this horizontal line segment, because do I take this endpoint or do I take this endpoint of a horizontal line segment? In this case, actually it turns out that I will need to do something a little more complicated. For every horizontal line segment, I cut it into 3 parts: a left part, a right part, and the middle part. The main thing about the middle part is that it spans a bunch of slabs, whereas the left and the right part have exactly one endpoint inside a slab, or they could have both endpoints inside the same slab. So when I do this splitting, I only split the endpoints and not the middle part. So basically I delete the green parts of all the horizontal line segments, then I do this kind of splitting. So basically when I split the input into these chunks, I split them without the green part of the horizontal line segments, and therefore now every horizontal piece can exactly go into one sub-problem. So all of these pieces that are in this shape, that in this slab, for example, they can go to this part of the input. Everything over here can go to the next subproblem and so on. And of course, all of them will place on the disk. So this is distribution. Then we recursively solve the problem inside every slab. So we find all these intersection points inside every slab. And now we are done, almost done, except for the part of finding the green intersection points. Okay. And the idea here is that we want to do this in using a sweep line approach. And the idea here is that if we assume that the input is now sorted according by y coordinate, then I can find the intersection point of all these green chunks with these vertical line segments in scan time plus output size divided by BIOS. And if I can do that, then the entire thing will run in sort time. Why is that? Let me quickly go back. This is because after finding this part in scan time, essentially I could just delete them and I will have a recursion. The recursion is on a subproblem that has size and m over b factor smaller. So therefore the depth of the recursion will be log base m over b of n over b. So therefore I will need to run this sweeping approach that many times. And if each time that I run it takes n over b IOs, then I'm essentially done. So the main complication here is how to do this part.